Okay, we are looking this week at ARMS interrupts and ADC in particular. Uh, there's the ability to handle 240 different interrupts, and there's a piece of silicone called a nested vector interrupt controller, and it takes the different interrupts, allows you to set the priorities for the different interrupts, and then it will pass to the ARM chip if an interrupt occurs, what the vector table number is. The ARM chip goes and it looks in that vector table, which was in that startup file, and it finds the address of the interrupt service procedure, and it goes there and handles the interrupt. And then if there is a number of interrupts that are queued up, it again arranges priorities and sends, as soon as that interrupt service procedure is handled, sends the next one off to the ARM chip. So it's a little bit different from the way that you've been used to it on the PIC microcontrollers, for instance, in which case there is a high and low priority, and you can go to one of two different addresses, and then you poll for what's most important. In order, from the difference from this lab, from the last lab, is we set up an ADC, and you would do the ADC start, and then you would wait by doing a poll for conversion. And it's kind of nice, that function, if you actually go in for the poll for conversion, checks, for instance, the flag, but we'll also have a timeout, so you're not stuck there forever. If some reason the conversion's never coming, that you won't just hang up your code. Um, with our interrupt, the whole purpose of wanting to use an interrupt is I don't want to sit and wait anywhere. I want to go and run my main code, my main while one, and the interrupt will give me a notification that the conversion is complete and to go do something with it. So I don't poll for conversion. And so here we do a HAL ADC start, but instead of like we did for a poll, we do start IT, which says, hey, runs the appropriate setup to be able to have the interrupt flag fire and jump to the interrupt service procedure. In our graphical setup, it's just a checkbox. You say enable IRQ, and it's going to put the required interrupt service procedure handler in the it.c file. And then so you go down there and look at it. One of the things that it has also done, this handler, so you never call a handler. You don't, in your code, call ADC IRQ handler. As part of the interrupt having fired, it will go to that interrupt handler. Okay? And so all I'm going to do in my main code is go HAL start, HAL ADC start IT, and then as long as I had that checkbox set up, then when the interrupt fires, I'm going to that routine. Yeah.
I just having trouble with the variables to plug into those, each of those. Are those that we just copying them directly from the table?
No, if you go HAL start IT, for instance, and you go control space, it should say I have the address of handler 1 or handler 3, for instance. So just like we did when polling, when you go HAL start and you go control space, it says, well, you've only enabled ADC3, so it's the address of ADC3. Here it'll be the address of ADC1 or the address of ADC3, and you have to start each one. Now it's going to jump to the same interrupt service procedure because there's only one for the ADCs. And so you'll see in that service procedure that it does a call to handle ADC1 and handle ADC3. In each of those, they have a HAL ADC conversion complete callback, and that's defined as weak because it's a placeholder because you might want that. And before they had that, what would happen is you would have to go to the it.c file, go find the handler, and put your code there, whatever you wanted to do. Like when I'm jumped there, I know a conversion happened, so you want to get the value. So you call HAL, ADC get value, for instance, or get conversion. I can't remember. Is it get value? I have to look. Okay, and so you you would normally have to do that in the it.c file. And so let me maybe fire that up. So if I have something in one file and I wanted to talk to something in another file, then one of the things that you would do, for instance, is you would say I want everything defined in main. In main, well, just above main in your main.c file, you would put a global. And let's say I have an int. And so if you have an int called my value, figures, my ends rect. If you have an int called my value and I said it equals to 0, for instance, then that's in your main.c. In your it.c file, if you want to reference it, you put it up at the top of the file, and you don't put equals 0. You don't, because that'll give you you're trying to reinitialize something you've already initialized. You just put an extern in front of it. And what that tells the it.c file is, it's not here. Don't give me an error. It's defined somewhere else. And then the linker goes and matches all the things that you promised would be there versus what is there. Okay. And so that puts it all together. So in it.c, I put an extern. Okay, my marker's completely gone. And don't initialize it. And over wherever you wanted to originally define it, like I said, at the top of main.c, that's where you say int my value equals 0. Okay, so int my value equals 0. If you're using it in main, well, it was defined there. If you're using it in it.c, the extern says it's not here, but don't give me an error. I know we'll match it up later. Okay, so that's how those kind of work. If I have it in here. So I have this IT file. I don't know if I generated it from the last time that we were doing it. We go all the way down. So by the very fact that I just checked that box over in the IOC file in the graphical interface, I went to ADC3 and I checked the box. ADC1, by the way, will also be checked off because if you said it's going to use interrupts, then your ADCs are going to go and generate the one IRQ handler. So here, when I've initialized ADC1 and ADC3, you have the IRQ handler and it passes in the address of the instance of the handler for ADC1 and ADC3. So it did that automatically by me doing the checkbox. Then in order to use it in main, you have to go how start ADC IT and say you want to start the instance of ADC1, address of HADC1 or address of HADC3. You have to start each one. Now, I don't want to wait, so I don't want to poll for conversion or anything. The whole purpose of this is the fact that as soon as I get a conversion, it's going to jump over here. And like I say, you used to have to put your get the value right here. So I would put it in user begin ADC IRQ1 and so after it's gone and done things, go get the value, put an extern at the top, put a global over in main, and go and pass the values back. Because everybody wants to do that. The documentation has said, hey, there's also this conversion complete. And so they put that in as a helpful thing. So you wouldn't have to go through that whole thing. And it says HAL ADC conversion complete callback. So if you stick that in the bottom of main at your user begin and fours, then as part of each one of these, as part of this calling this, if I highlight this and go through here, it will call the conversion complete and it passes in that it's the instance HADC1 or it passes in that it's the instance of HADC3 and it calls both of them call that callback. So in our main function, I don't think I put it there. Well, maybe I have. Let's see, way down at the bottom, someplace where we can go and put things. So I have the HAL ADC conversion callback. And I found that because I opened up the declarations and went to find where the prototype was. For instance, if I go it.c and I look at this and I go, well, I know it's in there. I can highlight it. You can either hit F2 or you can start scrolling down through it and find it. Or if I open this and I go right click and I go open declaration, that should open where the HAL ADC IRQ handler is, and we go looking for conversion complete callback. There it is there, and I grab that and I right click and I go open declaration. And the only reason I want that is to find as weak because I might not use it, probably haven't used it, but if I do, you just copy that and you stick it in main at the bottom here. Okay, and so there I can call just like you did in the polling one to get your value. And so I could, in this case, it's going to call for both ADC1 and ADC3. And so I might have thermistor value equals get conversion, and I might have the die temperature because I'm having you get the internal die temperature equal. Now, in order to tell which one's which, you could do something like if HAL, this is going to pass, HADC3, this is going to pass HADC, and I want to see if it's equal to the address of HADC1 or if it's equal to HADC3. Okay, and because it's passing that to that pointer there, the handle type def. So I'm going to say, hey, is it equal to one or the other? And then do the right conversion. And that's it. Okay, so up in main, I don't do that poll for conversion. What I had you do was blink a light. Yeah. Yeah, you're going to have to pass those up because it's not returning anything. So it either has to be global or you pass a pointer. Okay, either one. One of the things with, right, and I know normally you don't want to pass a global, but if we want to use our debug feature to pass things up, it'll go in and out of scope unless you do something like that. So it's easy just to put it as a global for now, and don't tell Phil or Wayne or anything like that. But just for the debugging, in the end of things, and everything's all working right, you might just want to pass with a pointer. But because it's a void, you have to do something like that. Okay, so that's how we do that. And then up in main, then I'm not doing this. I just copied over my project. That's why poll is there. I no longer poll. And so we won't do that. The other thing is the interrupt service procedure that is in my it.c file. This is called as a result of the flag happening because the conversion was complete. The CPU jumps there. You don't call it. Okay, it's an interrupt service procedure. So, but it will call as the result of that happening. And then, so I don't want to get the value here because it's not ready yet. Where is it ready? It's in main, user begin for and end for where that conversion complete callback. So get therm value if it's ADC3, get die value if it's ADC1. Okay, you just copy those and put them in the right place in the conversion complete callback. So right there, HAL start ADC 3, HAL ADC start address ADC 1, and then you would, so you start both, then you would blink a light or something like that, and then it's going to get the values in conversion complete, and then so you have therm value and I don't know, die value, and then you do something with that, print them out or what have you. Okay, and then it's always good in our case again to have a delay. Have a delay of 200 milliseconds or something going through the loop. If you just, and it can happily just run and blast stuff out, but if you're having the data going through the debug channel, you can fire data out far faster than it can print it out on the screen. And so it says buffer full every once in a while, and it'll give you an error and pop up, and you have to close it off and things. Just put a delay, and it's happy to keep up with what you're doing. Yeah.
How fast will these conversions be completed? Like how fast, how many times is that interrupt going to be?
A lot.
Maybe dependent on the delay there, or no?
Yeah. This is the deciding factor. It's way over. You have um, it's 1.2 million samples per second, but you can daisy chain three of them and get up to 7.2 megasamples. And so, yeah, it can happen lots. So when I say, for instance, my pull for conversion address H80C3, 500 milliseconds, it's done almost by the time it gets to the next line, right? So the I just want some sort of delay there to say, okay, if you hung up, don't wait there forever and then come back to me. But it's, um, I believe 1.2, we'd have to look in the data sheets, I believe 1.2 million samples a second to begin with, but you can daisy chain the three of them if you want to increase your rate. So in other words, the sample and hold is working on the um, second one while the conversion is happening on the first one, and then the sample and hold capacitor for the third one is working when you're doing the conversion for it, so you can chain them up if you happen to need a faster, and we're willing to give up the three in the case of reading one input, for instance. Okay. Um, any other questions on that? So we're using the ADC, but the point is that we're looking at interrupt service procedures, and there's all sorts of different interrupts. There's for talking I squared C, UARTs, different timers, all the rest. And when I go and enable the interrupt for any one of those in the graphical interface, it will stick in the IT.C. It will stick another handler. One of the things that it did just as part of the setup, it used the systic handler. And I said that when you set up the clocks, by default, the environment is going to give you a system-wide timer called systic that happens every 1 millisecond. And it knows whether you're running 168 megahertz or 40 megahertz or what have you, and it will arrange all the scaling factors and set things up to give you a 1 millisecond system interrupt. So I can use that for operating systems because if I do a HAL delay, for instance, currently we're just sitting there, but I could have my operating system go and do other things. So when I go HAL delay 200 milliseconds, it's running at 168 megahertz. It could go service other things. And we'll talk about some of that stuff more when we go into operating systems. One of the things in this class, though, is that systic happens every 1 millisecond, and then it increments this count, and it gives you places for your data as well. So I could do something. I could put a count in there, for instance, and do something every so often. For instance, I could count up to 500, set a flag, so make it, a static int count equals 0, and then go count plus plus. And every time it gets to 500, set a flag, and then reset your count. And so you could, for instance, do something, and in your main loop, just every time the flag is set, toggle a light. That's one way of doing things, okay? If you didn't want to interrupt your main flow of code, okay? Fact is, systic happens every millisecond. You're going there every millisecond. And so you could do something with it if you wanted. Or just in your main routine for now, you could go, HAL delay 250, set the light, HAL delay 250, clear the light, or 500, or whatever you want to do. Um, we're not doing too much in main, but I wanted you to flash the orange light. So again, you could just do the HAL delay in here, toggle a light, then go get your values. So turn it on. A HAL start IT for both of them. Toggle a light. You know you're done. Get the values, print them out. And if you're putting a delay up here for your light, then that's going to slow things up enough that you wouldn't necessarily need another HAL delay 200 at the bottom. You're doing things slow enough that it's not going to overflow that debug buffer. All right. the how many ARM chips do you think are out there in the world?
These two.
At least, well, there's at least 30 or something. Yeah,
Billions.
yeah, billions. And it's ARM. When they started out, the ARM was originally Acorn Computers, and in Britain there was uh, part of the television BBC. They wanted people to be able to play with computers, and the Acorn Computer Company got the contract to build the BBC microcomputer, and they'd have a television show, and you could sit down and watch your TV and learn how to program computers with the BBC Micro, and it was really, really popular in England. And as part of kind of that thing, um, around that time there were VIC 20s and Commodore 64s and like I say BBC Micros in England mainly, Great Britain, and you know back in those days you'd roll up your sleeves and you'd build a modem interface and you'd maybe solder some stuff and over over the years um, computers got more powerful. In schools, it got from rolling up your sleeves and writing code to the computer class was learning Word and Excel, and that was it. And then a few years ago, actually, there was a big initiative again where the a couple of founders of the Raspberry Pi Foundation wanted to get back to that BBC Micro Day where the schools all had computers and there were parts lying around and people built stuff and wrote some code and all of that. And so they came up with the Raspberry Pi, which is a nonprofit organization, and they convinced people to build the Raspberry Pi machine. And all of a sudden, that's gone everywhere, and it's gone into schools, and it's gone more with you have some LEDs and some servos, and you do kind of things with it. So that's all coming from that original kind of excitement and spirit way back when, and that got lost with your computer classes doing some word stuff. And so, but way back in that kind of time, they had this BBC microcomputer, and they made the first ARM chip was I think originally called like the ARM 2, and it was a kind of a collaboration between this Acorn company that made the BBC, and then they changed the name from Acorn Risk Machine to Advanced Risk Machine, and it became what we know as ARM, and they made the ARM 2 chip. And it was a collaboration between this Acorn company and Apple and a company called VLSI, which made the semiconductor materials, and they kind of put this arm together. And they made that was around. I don't know if you're around the time of Apple Newton. Apple Newton was way before its time. It was a PDA that didn't quite personal digital assistant that didn't quite do what it was supposed to do because the technology wasn't there, but it was a really cool idea at the time. Um, a real precursor to digital assistants and then smartphones and that kind of thing. Um, but after the ARM2, then the Advanced Risk Machine company decided that you know they have a really good kind of design for this ARM, and what they would do is they would license the core, the intellectual property of their design and the instruction set to other companies that wouldn't actually make anything. They just license it. And the ability, the idea of that, and it was pretty new at the time to be able to just say, we'll just license you intellectual property. We won't actually, give you any real hard substantive thing. We won't manufacture anything anymore. Just license this technology to you. But the idea would then, Apple, for instance, could license the core and then do their own thing with it. And ST did, and Philips did, and a number of different companies said, we'll take the core so we have the instruction set and we can do things with it, but I want some more serial ports on it. I want more memory on it. And over time, the architecture changed into different families because when I have a smartphone, I have maybe different needs than if I have a microcontroller. So we're using the ARM Cortex M series. Before that, there was the ARM 7 series, which was used in the Nintendo Game Boys and things. And then when you are in a smartphone, you're kind of more in the ARM version 8 architecture or the ARM-A architecture. And so there's different families. It all started with this one core, and then different industries needed different things, and they changed and advanced. Okay, the ARM V8 stuff is capable of doing the 64-bit, whereas the ARM Cortex M series is a 32-bit. And then you have all of these different ones. So when you just see ARM, there's a bunch of different families. It has evolved over the original thing. So as far as numbers go, and I heard billions. Is that right? Billions? Um, the Let me see if I've got, do I have my picture? Okay. So yeah, it's billions. Just over the last quarter, final quarter of 2020, they shipped 6.7 billion in the quarter. They have shipped over 200 billion right now. So when you think of what is there, 7 billion people in the world, they have 200 billion of these things shipped there. And that's why we wanted to talk to you about ARM. They're in everything. Okay. And so and one of the things is when this whole thing started, x86, the PC market, and so Intel and Motorola had different. We're all competing for the desktop marketplace, and Motorola was very much involved with Apple, and so the Motorola chips were in all of Apple's computers, and the Intel x86 type stuff was in all of the Intel type PCs, and so that was the way things were, and they were both, would up their speeds and how much memory they could have and all of that. But then you had laptops came along, and so you needed power for computing and things, but then you also needed to really be miserly with power so that you would have battery life. And so, yeah, how do you get the speed but reduce your power consumption? So they developed different chips, and Motorola just couldn't match Intel at the time to such an extent that way back, Apple moved over to the x86 chipset because they just couldn't compete in that market with the Motorola chips. So the whole time that all fight was going on, you have ARM just licensing their IP to everybody. And they're not competing in the desktop market in anything, but if you want something in anything else, like you have DVD players, and you have GPS units, and you have into your phones, and you have you name it. There's probably an ARM chip of some variant in behind. So they were just licensing, not making anything. Just I'm going to say you give me $100,000 up front and $1 for every chip that you make, kind of thing. Awesome. Okay, and that's worked well. In fact, a little digression, Microsoft became the juggernaut they are because way at the start, they had IBM or they had Microsoft DOS. IBM said, hey, do you have something? We're going to come out with an x86. And they came to Microsoft, and Microsoft, what Microsoft said when IBM said, hey, because Microsoft was selling BASIC. They sold BASIC everywhere. That was their thing. And IBM came to them because they were going to, I remember Byte Magazine in, I think, 1984, and it said, hey, they're going to come up with this x86. They went to Microsoft because they were in a lot of machines for their basics and said, hey, do you have something for us? Microsoft said, nope. Go down to Digital Research, guy named Gary Kildale. He's got this CPM. Go see them. And so they said thanks, and they went down to see Gary Kildell, who happened to not be there at the time. Some of his other people were there, and whatever happened, Microsoft came back and they said, we don't want to deal with those guys. Are you sure you don't have something? And it so happens, Seattle Computer Products, there was a little, everybody would get together with their Commodore 64s and TIs, and they would all be doing kind of computer club things. And somebody was working on a CPM like system. And Microsoft said, hey, can I buy that off you? And the guy was going, you're a little store and you need the money. And so, he bought this CPM like system. And then he went back to IBM and he said, hey, I have something for you, but he really wanted basic and stuff to happen. And he said, hey, I'll give it to you as long as you put basic in the computers. Because then if IBM's using his basic, then I can sell basic to everybody else. So IBM gets a free operating system. Microcomputers, PCs, it's a fad, and it's going to last probably 5 years. We'll maybe sell between 500,000 and 5 million, and then it's done. So we'll take, because mainframes and mini computers are where it's at, but we'll get some money out of this fad. So they said yes. And then Bill maintained rights to be able to sell it to anybody else. So when the market started coming and people wanted IBM clones, they needed an operating system. So they go to Bill and they say, do you have an operating system? Yes. I'll sell you MS-DOS. PC-DOS was the free one IBM got. And even into the Windows times, if you booted up a computer, if it was anybody else's computer, it would say an error message, no ROM, system halted, no ROM basic. And you go, what the heck does that mean? Well, it was looking for Bill's basic. It'll try to boot off the C drive, the A drive, can't find things, it'll boot off the basic, and it's not there in other machines. Used to have a little socket for it, but then that disappeared. In PC, in Intel IBM machines, what would happen is it would try to boot off A, would try to boot off C, and then it would go in and give you a little prompt. And you can actually go 10, print hello, 20, go to 10, run, and it would run because it had it in there because they weren't paying for their operating system because that was the deal that they made. Anyway, so when other companies came around, what they did, Bill says, the licensing agreement is to make it easy so we don't have to keep track or whatever, you just pay me $100 a machine that comes out of your plant, for instance. So that makes it easy. You say you made, 10,000 computers, 10,000 times 100, you send me the check and we're all good. There is no competition. There is nothing else. So everybody signed on the dotted line. It wasn't until years later that that was deemed anti-competitive because other people, digital research, the same ones that Bill sent them down to, I came up with a better version of DOS. They came up with a multitasking DOS. You could do many things, and it was only $60. But all of these companies are going, but my agreement is every machine that comes out of my plant, I send Microsoft money. So it doesn't matter if you're giving it away or what have you, I'm still paying Microsoft. So, that kind of thing. That's a real digression here, but that was this kind of licensing thing. They do the same thing. They say, give us an upfront sum, and then it's however much. And that's been working well for them. And again, 6.7 billion chips. Everybody gives varying degrees of money over to the ARM company. And one of the interesting, ARM has been bought and sold a few times the last few years. SoftBank owned them for a while. They're the same guys that bought the, I don't know, killer robot dogs or whatever from that company. Boston Dynamics. Yeah. So they have them, but Nvidia just picked them up, and so that's kind of cool. So you're looking at, like I say, 6.7 billion just in the last quarter. And let me just okay. Oh, okay. We'll see if my internet and not going. Yeah. don't know why the internet at the end of the class every day seems to go that it's like, yeah, I don't want to. Let's see if it'll do it. So the latest things that I see is from the last quarter of uh, 2020, and it said it was at about 180 billion, but they've been doing, 6 to 10 billion a quarter. Actually, one of the last quarters they did was 22 billion processors. And one of the things, let's see if I've got it here. We're on D, no, don't have it. One of the big users of processors, and it's hard to find um, cars. And when you look at cars from 2000 and, well, really 2002 on, the number of processors and things have increased dramatically. In fact, one of the problems that we have with the um, uh, used cars prices are up. People can't get new car prices are up. There's a real shortage everywhere, and one of the problems is the chip shortages. And depending on what you hear in the news, for instance, everybody wasn't going anywhere, and they say that manufacturers retooled for like game consoles and all of that kind of stuff. I don't know how much is the news or the truth, but there is a chip supply shortage. And so, for instance, Ford trucks, they could only produce so many because they couldn't get the chips. And if you look, I've seen anywhere from them saying 50 microprocessors in a car, and I've seen all the way up to 1,000 microprocessors in a car. So it's just crazy. But if you look at most chips, for instance, if you look at microprocessors to make a smart sensor, like we're looking at a Cortex M4 chip. It's probably about $6 single user quantity. But the smaller versions of that, you can get below $1. And if you look at a 32-bit microcontroller, you can hook some sensors on and then run some code on in a sub-dollar chip. That means everything can have a communications protocol, and in cars it's CAN bus that you can talk and relay messages to. So they'll have a central kind of computer that runs everything, and then they just interrogate the indicator lights, the sensors to say that is there a young child in a front seat? Should the airbags be deployed or not? The whole airbag sensor, accelerometer, did it take off? All of that stuff. They just have individual microcontrollers with these modules that you can then pull in and replace. And so, like I say, if you go searching, it's hard to find how many microprocessors are in an F-150. Hard to find the kind of numbers. The things I've seen, like I say, some say, oh, there's 50. I've seen some say that some cars have up to 1,000. So there's a heck of a range there. Even if you say 50 microprocessors for each, don't forget we said there's just in ARM chips, there's 200 billion. One of the things, though, there's also a different kind of need for the chip that is in and on the link, if it came up on with the college, the other link I have over there, it's talking about the automotive industry. And for instance, mean time between failure in a microprocessor has to be greater than like 15 years in an automotive, whereas they're saying it's 5 years in a standard thing. So the requirements for the chips, the hardening of the chips is so much greater. They don't want you to have to, throw out your car in 5 years. It has to last the duration kind of thing. Uh, so we have that. I have a bunch of links for talking about the different architectures and things on here. So this is Wikipedia. And so I have a whole page of a bunch of different links. And so, again, ARM was originally Acorn RISC Machine. and it's now advanced RISC machines. And RISC stands for reduced instruction set. And it used to be talked about more, but when you see a RISC machine, it's a reduced instruction set computer. And the idea behind a RISC is that if I have fewer instructions, the silicon is smaller, I should be able to run things faster, and I will make up for in instructions what would normally be in a more complex instruction set. And so maybe with a smaller instruction set, I have to run 50 instructions to do what you could have done in one, but I can run them really fast. Yeah.
Is it used for data management too, and like filing? Or am I getting that mixed up with something else, like RISC-V, RISC-3?
A RAID.
RAID, sorry.
Yeah. But there is a RISC-V, and I want to talk about RISC-V when you bring that up. But yeah, so reduced instruction set means, and we used to have this company called Xenix that would compete with the PIC microcontroller, and they would run one instruction in 10 nanoseconds. And so you could run at 100 megahertz, divide by one. Do you know how many instructions, what does it take to run an instruction on a PIC? Do you know? So you were running at, let's say, 20 megahertz, divide by 4 is 5 MIPS, so you're like 200 nanoseconds in instruction. They could do it in 10, okay? That's a propagation delay of an AND gate, going from input to output, one instruction. And so they said they didn't have any of the serial ports. In a microchip, you have serial ports. It's a hardware module. Well, they said, yeah, don't use that silicone. Just come up with instructions and do what's called bit bang it. So I will just time the I/O and make the inputs work like a serial port. I can run fast enough. I have the propagation delay of a gate on an instruction. Okay, and so with reduced instruction set, you can maybe get away with that kind of thing. You have fewer instructions, you run them faster. CISC, complex instruction set, like Intel and things, you say, I have a need for a certain thing, I'll put instructions that do that, so it's one instruction. One of the things about that is that different architectures have different machine language instructions, and if your operating system knows what you have, it can take advantage of that and run faster. So if I have a generic, for instance, Linux, for instance, kernel, and it's running on just a machine, it thinks, okay, base, kind of 586 or instructions. So I won't use anything that's optimized, but you could recompile it and take advantage and get more throughput. But it can't just by default say, I'm going to just work on something with an NVIDIA card in it or something like that, because not everybody has it. So you do the base, but you could optimize, okay? One of the things about RISC is the first PICs that were out there were really reduced instruction set. They had 32 instructions. The ones that you used had about 78 instructions. Okay, so that's still reduced, I guess, but it's more. When you look at the ARM chip, it's really hard to find depending on which one, and we're the M4, which has digital signal processing instructions on the top, but you're 230, probably something like that. You look at an Intel, it's looking at, I've seen, it's really hard to base depending on what you call exactly an instruction with all the different options they have, but anywhere from 1200 to 2000. So quite a bit different depending on which one it's optimized for. But the terms have gone, because it's like 32 instructions, I'd say that's really reduced. When we get to 200, how reduced is that? I guess it's reduced over, 1200 instructions, but it's lost a little bit of the meaning. The other thing I wanted to, what type of architecture was PIC? Wayne would have said some names, I'm sure. Your code space and data space was separate. What kind of architecture is that? You have Princeton, von Neumann kind of thing, that's one, and you have Harvard. So again, PIC use separate code and data spaces. That's a Harvard architecture. Motorola, for instance, the Motorola 68000 was Princeton, also known as von Neumann, and it used everything. Your code space was the same place as your data space. And again, those words, it's good to kind of recognize where they come from. They've kind of lost a little bit of meaning because actually, when we looked at that big picture of the ARM, it had separate instruction and data spaces. So it's Harvard. But when we go and look at the memory map, everything's in the same address space because they've mapped it into the same area. They're in different physical places, but as far as you're concerned as a programmer, it's in the same 4 gig linear address space. So it's kind of lost a little. They called it a Harvard bus architecture. It is separate in places, but everything's mapped into the one address space. So some of these terms that you see are kind of falling by the wayside a little because what's reduced, what's complex, and how reduced is it? 32, I think, is really reduced, but 200, yeah, okay, it's reduced more than somebody else, but you know, uh, um, it's kind of like you're saying 30% less sugar, than what? A bag of sugar? What's it comparing it against? So, okay. So, but those terms are out there. We are known as a Harvard bus, but we see everything in one address space. Okay, even though behind the scenes it does it different. We are technically we are reduced. It's a reduced instruction set, but it's going to be way more than your pick and things like that. We'll continue talking next day. Thank you.